We are living through an absolute paradigm shift right now, a technological leap so profound that it's literally rewriting the rules of how we invent the physical world. Welcome to this explainer, where we're going to dive into how artificial intelligence is fundamentally breaking the historical bottlenecks of materials science. I want you to imagine waking up to find out that artificial intelligence just discovered 2.2 million new crystal structures, literally overnight. That number completely shatters the scale of known stable materials. It's like suddenly finding a map to millions of new islands when we only ever knew a few thousand existed. To truly grasp why this is so shocking, we kind of have to look back. For centuries, dating all the way back to pioneers like Marie Curie, discovering a new material was an agonizingly slow process. It relied heavily on pure physical intuition and, honestly, massive amounts of tedious, trial-and-error experimentation in the lab. Let's look at the evolution of discovery paradigms. From Edison testing thousands of different light bulb filaments to modern supercomputers running incredibly complex physics simulations, researchers have historically been trapped in what we call a forward design process. Basically, you guess a chemical structure, you synthesize it, and then you test it just to see if it does what you want. As you can imagine, it is incredibly slow. But here's where it gets exciting. We have officially entered the era of inverse design. It's an entirely flipped approach. Instead of guessing a structure and hoping for the best, we start with the exact physical properties we want. Then the AI works backwards to generate the exact molecular structure needed to achieve those properties. Think of inverse design like reverse engineering a baking recipe. Instead of blindly throwing ingredients in a bowl, baking it, and tasting the results, you just tell the AI, hey, I want a cake with exactly 150 calories and a rich chocolate flavor. The AI explores a massive, high-dimensional design space and spits out a precise, never-before-seen recipe to perfectly match your request. Now, traditional AI actually struggles to comprehend 3D space. So to pull off this computational magic, engineers use graph neural networks, or GNNs. Because these models treat atoms as nodes and chemical bonds as connecting edges, they natively understand the complex spatial constraints of physical materials. This allows them to rapidly calculate exactly how a material will behave under stress. A perfect prime example of this is Google DeepMind's Graph Networks for Materials Exploration, or GNOME for short. It acts as this massive data flywheel, generating candidate structures, predicting their stability, and filtering out the bad ones. It's evaluating millions of structures in a fraction of the time it would take a human researcher. And the results? By mapping out these structures, the genome model expanded the number of known energetically stable materials on the convex hull from roughly 48,000 to over 420,000. That is an absolutely unprecedented order of magnitude leap, delivered almost overnight. Now, you might be wondering, are these just virtual hallucinations, math errors? No way. These beautiful atomic configurations are physically viable. In fact, over 700 of these AI-discovered structures have already been independently synthesized in real-world laboratories. The AI is making predictions that actually work in physical reality. But it goes beyond just crystals. AI inverse design is being used to engineer wildly complex metamaterials. Algorithms are discovering microstructures that are simultaneously incredibly stiff, meaning they have a high Young's modulus, yet perfectly block heat transfer. That is a paradox. It's a combination notoriously difficult to find in nature, yet AI optimization algorithms are generating them right from scratch. This technology is absolutely supercharging aerospace and advanced manufacturing too. Algorithms can now tell automated robots exactly how to weave and 3D print continuous carbon fibers for maximum strength and low transfer. It's essentially mapping out the exact stress-strain curves required for a part and designing the microscopic lattice to match it perfectly. As one paper points out, AI presents significant potential to expedite the exploration of this extensive, untapped space.
By perfectly integrating artificial intelligence, architected materials, and additive manufacturing, we can finally navigate the nearly infinite design space of customized composites. We're moving from off-the-shelf materials to materials designed pixel by pixel for a single specific task.
Now, while this massive computational leap might sound a bit intimidating, AI isn't here to replace engineers. It's the ultimate co-pilot. It handles the billions of repetitive quantum calculations so human researchers can focus on what they do best: physical synthesis, testing, and applying these new materials to solve real-world problems like clean energy and microelectronics. We are standing at the edge of a completely new industrial revolution. With centuries of frustrating trial and error now compressed into just days of computation, the only question left for the next generation of scientists and engineers is this: what revolutionary material will AI help you discover next?